I actually don't know how to use this. It's not working. That's fine. I can just click. Okay, sounds good. Okay, so yeah, thanks everyone for coming. I'm Noah. I'm at CMU. This is joint work with three wonderful collaborators, Meghal Gupta, William He, and my advisor, Ryan Madam. Okay, so I'm going to tell you a little bit about a problem that many of you have probably heard of, which is the max kXOR problem. So in this problem, you have a bunch of 0, 1 value variables, or actually plus minus 1 for this talk, and you have a bunch of constraints. Each constraint takes some set of the variables, multiplies them together, and then tells you it has to either be plus 1 or minus 1. So yeah, n is the number of variables. I'm going to use k for the number of variables which is in every constraint, which people also call the arity. And m is going to be the number of constraints. So those are the three numbers we sort of care about. And I encourage you to think about an instance of this problem, a list of these equations, as sort of a hypergraph problem. So you have m hyperedges. You have k vertices in each hyperedge. Each hyperedge tells you which variables you're multiplying together. And then in addition to this list of hyperedges, you have one bit, a plus minus 1 bit, labeling every hyperedge, telling you is the product of the variables in this hyperedge supposed to be -1 or +1. Okay, so I'm going to be talking about sort of average or semi-random versions of this problem. What this means is that I'm going to be talking about models where you're given a worst case hypergraph G, and then you're trying to generate these right-hand side plus minus 1 labels for all the hyperedges. So the quote-unquote null model for this problem is just uniformly, randomly picking the right-hand sides for each equation. So what this means is, yeah, you have these sets of variables. For each one, you independently pick a plus minus 1 label. And a standard fact about this kind of model is that as long as you have a linear number of constraints in the number of variables, then it's very likely that every possible assignment is bad. So every possible assignment will only satisfy roughly half the constraints, which is what a random assignment would satisfy. Also, this uses like m bits of randomness to sample these right-hand sides. Okay. Another model for generating right-hand sides is what we'll call the planted model. In this model, instead of just sampling the right-hand sides, I first sample a signal, which is like a plus minus 1 assignment to the variables or the vertices, and then I'm going to pick right-hand sides that are consistent with this planted signal that I found. So for example, here are the 7 vertices variables. I sample a plus minus 1 label for each one, and then when I'm trying to decide the right-hand side of the first equation, I just like look at what are the 4 variables that were in that equation. I multiply together -1, -1, +1, -1, that's -1. So I put a -1 there. And I do the same for every equation. So this model uses n bits of randomness as opposed to m on the previous slide, and it has the property that there now exists a assignment x which satisfies every constraint. So this is a strong contrast to the previous slide. Okay, so roughly the computational problem I'm going to be interested in is the complexity of distinguishing the right-hand sides if you draw it from the first distribution versus the second distribution. Okay, but there's a slight catch, which is that there's actually an easy way to tell whether or not there exists a perfect assignment x, which is just Gaussian elimination. So that's a picture of Gauss from the internet. So if you just like sort of greedily use all the assignments, you can derive what x actually has to be as long as you have more than n independent equations. Okay, so instead of asking to distinguish planted and null right-hand sides, I'm going to ask to distinguish null and hybrid right-hand sides, where hybrid means with some small noise probability like 1%, I take a planted right-hand side, otherwise I just take a uniformly random null right-hand side. So this is a computational problem. Can you distinguish when you have uniformly random right-hand sides versus when you have some slight signal correlated with this underlying hidden assignment x? Okay, so what is the complexity of this problem? It's sort of well known to people who study these sorts of problems that if you're looking at kXOR, then as long as the number of constraints is roughly n to the k over 2, maybe there's some log factors that I'm hiding, there are polynomial time algorithms for these types of problems. And about 6 years ago, it was known, oh yeah, sorry guys.
So I had a question regarding the hybrid model.
Yeah.
Like, should I really think of it as still almost uniform, or like the percentages that you wrote there?
Yeah.
So
You can think of it doesn't. I guess like the interesting question. This problem only becomes harder when the noise rate gets lower. It's like the easiest case is when the noise rate is 0, or actually when the noise rate gets higher. I guess like when 1% is 0, this is as hard as possible. When 1% is 100%, this is as easy as possible.
Exactly. So I was just asking, like, you really need it to be 1% or something like 80% is.
No. 80% is fine. We can handle any constant.
Okay.
Yeah.
That's what.
Okay. So there's a sub-exponential time trade-off for this type of problem when the number of hyper-edges, the number of constraints, is between n to the k over 2 and n. So this is not my picture, but I borrowed it from a friend. But this is basically, when you have n to the k over 2 constraints, then you have polytime algorithms, and then it scales all the way up to when there's only n constraints, you need exponential time algorithms, and there's a sub-exponential trade-off, which is pretty well understood between these two extremes. Yeah.
So can I ask a few questions?
Yeah.
The first one is, like, if you don't care about computation,
Yes.
like, what is the sample complexity? How many constraints do you need to
I
see?
think you should only need a linear number of constraints if you don't care about it.
Is this also a lower bound that you need this many?
I think it should be, yeah.
I see. And these lower bounds are for like low degree polynomials. For what model is it?
I think, yes, there should be low degree. I mean, there's even SOS lower bounds for these. Maybe not the distinguishing problem, maybe for refutation problems that are related.
Okay, so
but I
it's
think this
basically
trade-off is.
for a restricted model of computation.
Yeah.
It's not like a reduction function. We
Oh,
don't
no,
know.
no, no. This is not known to be an NP hard, but I think it's like believed that this is the best possible. Yeah. Okay.
I mean, the reduction could have been from some average case hard problem. It doesn't-
Yeah, but I
doesn't
don't think
need to be,
that's-
but
I don't
it
think
doesn't
that-
exist.
yeah, I don't
so
think so.
we just believe because of the low degree
Yeah.
or SOS hard that this is difficult.
Yeah, exactly. Okay. And then from this year, last year, there was this paper, Schmidt, Huber, and Ryan, one of our co-authors, and Quadratic and Babouche, who showed a quantum algorithm which is quartically faster. It's sub-exponential, but it's still quartically faster than the sub-exponential time algorithm that was known from this 2019 paper. And the main result of our work is a quadratically faster classical algorithm for this same problem, at least when the arity is larger than a very large constant. What this means is that this quartic speedup in this quantum paper is actually only quadratic, again, at least in the case where the arity is a large constant. And also, I will just say that there's some other, actually maybe I'll first say quadratic speedups are relatively common, so this may suggest that this particular problem is less promising from a quantum advantage sort of perspective. There's many papers along these lines where people think harder about a problem where you think that there's quantum advantage and then it actually turns out to be not as significant as it seemed. Although there's a bunch of catches here. So like our algorithm is better than the quantum algorithms in some ways. For example, we can handle a worst case hypergraph G where they needed a random one. But also the space complexity of our algorithm is sub-exponential and they have, I think, probably logarithmic space. So there's like large trade-offs that are sort of going on. And I just want to tell you a little bit about what this has to do with local algorithms.
So can I ask you again? So basically, you keep m to be n to the k over 2, and you just use the exponential to take the square root of the exponential.
Yeah, sorry. M is like m you should think of as, it's not k over 2. It's like m to the sum multiple of k between 1, where it's exponential time, and k over 2, where it's polynomial time. So like maybe m equals n to the k over 4 or something is interesting. So there's sub-exponential time algorithms. We get quadratically faster sub-exponential time algorithms.
I see. Okay, so you go below the polynomial regime.
Exactly.
For m, and you improve the exponential by a constant factor of the exponent.
Exactly, yeah. Also, this problem has been studied under other guises, like it's related to sparse LPN type problems that people care about in cryptography and some other problems. Yeah. So just very quickly, the ingredients in our paper, there's a notion called even covers and hypergraphs, which is sort of widely used for these sorts of distinguishing problems. And the main thing that we do that's related to local algorithms is give a quadratically faster algorithm for finding even covers in these hypergraphs. And even covers are sort of what you can use to distinguish. So maybe I'll just end the talk by saying what an even cover is, and then maybe you can ask me later if you want to hear about how we find them. So in a hypergraph G, an even cover is a subset of the hyperedges, such that if you look at the vertex indicator vectors for each of the hyperedges across the set, they all sum to 0. So here's an example. Here's the same hypergraph I had before. So I'm going to take a subset consisting of 4 of the 5 hyperedges. This subset has the property that, for example, if you look at vertex 4, it appears an even number. It appears 4 times, an even number. Vertex 3 appears also an even number of times. So every possible vertex occurs either 0, 2, or 4 times in this example. And what this means is that, for instance, if you look at the original kXOR problem I had before, you look at these 4 constraints that are forming this even cover and you multiply together the 4 right-hand sides, you get a -1. And if you think about the max kXOR sort of instance that corresponds to this problem, the fact that I have an even cover where the right-hand side's multiplied to -1 is like a certificate that this is not a perfectly satisfiable instance. If I take the four equations, I multiply them together, the left-hand sides all cancel to be +1 because I took every variable to an even power. The right-hand side is -1, so this is like a contradiction. And more generally, if you're thinking about these distinguishing sort of models, in the planted model, you always get a +1, sort of exactly for the reason I just said, because this is a perfectly satisfiable instance. So every even cover, the right-hand side is multiplied to +1. In the null model, it's like a uniformly random plus or -1. And in the hybrid model, and depending on the noise rate, it's slightly likelier to be a +1 than a -1. It's only likelier to be a +1 if I happen to sample a consistent planted right-hand side for every constraint in my even cover. So yeah, so the main thing that we actually do in the paper is give a fast algorithm for finding these even covers. And the way that this works, maybe I can just very briefly say, is that there's a graph called the Kikuchi graph, which people also study in this area. It's a graph that's related to the original hypergraph. It's a sub-exponentially large hypergraph. And finding cycles in this graph is basically equivalent to finding even covers in the hypergraph. And our algorithm uses sort of somewhat standard tools from sublinear algorithms, but in this new context, to find cycles in this graph in square root n time, which is like a birthday bound sort of argument. But this is now capital N, which is actually sub-exponentially large in the number of variables in the original problem. Whereas these, at least the original classical algorithm, instead of finding cycles in square root n time, took the spectral norm of the adjacency matrix of this graph, or the signed adjacency matrix, which is, even with the power method, is like a linear in n time. So yeah, somehow even though it's a sub-exponential thing, the sublinear in the sub-exponential thing sort of savings are coming from being able to find cycles using random walks and a birthday bound sort of argument. So that's why it has to do with sort of local algorithms. Yeah, so I guess like the actual trade-off is what's written here, but it maybe doesn't matter so much. There's just some trade-off, and this is what is sort of known. So yeah, that's it. Thank you. Yeah.
So, is there any regime where you could hope to break these low degree polynomial low bounds by just a little bit? I know that the degree there would be maybe omega of something, right? And you improve the omega. Right?
Yeah, I'm not. I'm actually. You mean the degree, like the arity of the? Sorry, what do you mean by degree?
So in which model are these sort of exponential lower bounds known? Isn't it?
So I think it's probably. I'm actually not even sure if there's a. I'm certain that there are lower bounds for the refutation problem, which is
refutation. Okay,
yeah.
For SOS, but for low degree polynomials, you can talk about the test.
I suspect that they exist, although I actually don't off my head. I'm not certain that they exist, but I think that they should exist for this type of problem. Yeah, go ahead.
Are there lower bounds for the complexity of finding even covers or like conjectures on whether it can be done faster?
That's a good question. I actually don't know. I think like even until a few years ago, it was not known that the even covers have to exist. Like I think this has only been known for about 3 years. So I'm not sure that there's a at least even covers definitely exist in a random hypergraph, but if you look at the setting like we do where you're starting with a worst case hypergraph and all you're assuming is that there's a sufficiently large number of edges, then the existence of an even cover has only been guaranteed for, I think there's this Guruswamy Kotari Manohar paper from like 2022 that solved that problem. That was like the semi-random version, but the refutation problem. So yeah, I'm not exactly sure what to think yet about the lower bound side of this. Yeah.
Can you comment on the size of the even cover that you find? Because if it's too small, it's only covering a few rules.
Yeah, actually, smaller even covers are better.
If there is, let's say, one even cover, that's...
Yeah, so, okay, this is a good question. So, I guess the ideal scenario would be finding many small even covers that are all disjoint. Because they sort of give you, like, if you're trying to, say, certify that the value is bad, like, you're finding many independent contradictions among the constraints. If you're thinking about the distinguishing problem, smaller is better because there's this noise rate, and then you're only getting contradictions if you happen to pick the you're only getting a signal if you like happen to pick the planted instead of the null for every constraint that's in the even cover. So I think what actually ends up happening is that we guarantee that there's roughly even covers of size log n, and I sort of hinted at but didn't say anything about there's like an exploiting the even covers aspect of this result where we show that it's sufficient to find even covers. All we need about the set of even covers that we find is that they're sort of distinct. So like obviously like finding the same even cover and over again is not helpful, but we don't need them to be like disjoint, or we don't need them to say not overlap. We just need them to be kind of different. And the reason that that's enough has to do with some other stuff that we have in the paper about some like polynomial anti-concentration sort of things, like even just having one variable in each even cover that's not in all the other even covers or something is still enough to get some advantage, at least for the distinguishing problem. Maybe it's harder for refutation, but yeah. That's good.
Okay, let's thank the speaker again.